Okay, so in algebra, we often solve one equation that has one variable in it, right? We solve for the variable. But then recently we solved two equations that have two variables. So we shouldn't be too surprised to see that we can also solve three equations that have three variables. And generally, you need as many equations as you have variables. Okay, so if you have three equations, if you have three variables, you need three equations. So let's look at these. We've already worked them out, so I put a box around the original problem, the system of three equations that we're going to solve. And we have the work here. So let's look at what we did. Now this first system is kind of simple, kind of nice, because one of those three equations is just y equals 9, this first equation. So that's pretty nice. That, for one thing, it's already solved one of the equations, right? And also that's going to give us something to substitute. So the method of substitution, which is the way we're doing this first one, it says solve using substitution, is actually more convenient than elimination for some systems. And we'll see this one, it works out pretty well. So we'll call this equation 1, y equals 9. So we'll call this equation 2, call this equation 3. So we can substitute, and we will substitute into equation 2, and that's right here. So we rewrote equation 2. No, wait, sorry, that's 3. We rewrote equation 3, which is down here, 2y plus 3z equals 15, but we put in 9 for y. So 2 times 9 plus 3z equals 15, since we know y equals 9. So then you can simplify, and the only variable in this is z. See, this second equation doesn't have any x's in it. It could, but I'm sorry, the third equation. Going a little too fast here. The third equation doesn't have any x's. So when we substitute in for y, the only thing left is z. So we have something with only one variable. And plugging in 9 for the y, we continue on and solve it. Okay, we get an 18. Subtract 18 from both sides, you get negative 3, and z is 1. So we already had y, and now we have z. Okay, that's right here. Only thing left is x. So we can go back to that equation number 2 that I talked about a while ago. It only has x's and z's. That's pretty convenient, because now that we know what z is, we can plug in for that z, and that's what we do. Put in a negative 1 for z, and then simplify it and solve for x, and x is negative 5. So when we do this way, the video is pretty fast because I'm not writing as I go, but you can pause it at any time. Go, wait a second, I want to see that, I'm not sure what he did there, and you can just pause the video. Okay, so we have all three numbers. All three variables are solved. We already had y. Okay, that's up here, is 9, and then we have z and we have x. So we can write them as an ordered triple. We're used to ordered pairs. Now we have an ordered triple. We put them in order x, y, and z. And so x is the negative 5, y is negative 9, and z is negative 1. Okay, just as we found. We have x there, y is over here, z is here. Okay, so let's look at another one, solved by substitution. Original system is in this box. We'll call this one 1, this one 2, this one 3, and they've been kind to us again. They have z equals 5. We can just plug that into one of the others, and we see the first equation has x, y, and z, so plugging in z for that wouldn't be real wise at this point, because we have a better one to plug into, which is the third one. It only has x and z, so we're going to be strategic. We're going to plug z into that one, and then we'll have an equation that only has one variable, x, right? So that's what we do right here. It's equation number 3. Substitute the 5 in for the z, and it was 2x plus 2z. It becomes 2x plus 2 times 5 equals 6. We multiply out the 2 times 5, subtract 10 from both sides, and divide by 2. So we get x equals 2. Okay, so we had z already, now we have x. There's only one equation here that even has y in it, right? 2 and 3 will not help us at this point solve for y because they don't have a y in them, but 1 will work, because 1 helps us because we know both x and z at this point. We already had z at the beginning right here. We just solved for x, so we can plug those both in and into the first equation, and then we'll have an equation that has just one variable left, and that'll be y. So we plugged in for x right here, we plugged in for z right here, okay, because z is 5, and the only variable left is the y. So simplify it. Negative 2 plus 5 is the negative 3, or positive 3. That's where we got that. Minus 5y is 3. Subtract 3 from both sides and solve it. You end up with y equals 0. So we have x is negative 2. That's right here. We have y is 0. That's right here. Second number in the triple. And we have z, which we were given at the beginning, is 5, which is right here. Third number in the triple. So we have this ordered pair and our ordered triple, and that's our answer. Okay? So now we get to the fun part. Solve using elimination. We have a serious system of equations here. All three of these equations have x, y, and z. So there's no easy solving by substitution here, right? They didn't give us z equals or x equals and a number like x equals 2. We don't have that. So elimination is probably the way to go in a system like this. It's done similar to the systems of two equations with two variables, but you have to chip away at it. It's going to take more work. So we'll first take a couple of these and try to get rid of one of the variables, and we see these first two. We'll call this one 1, this one 2, and this one 3. If we use those first two, we can add them, and we have a negative z in the first one and positive z in the second one, so that was kind of convenient. Add those together, it'll get rid of the z. That's progress, right? So now we have 2x plus 3y equals negative 3. We'll call that equation 4. Okay, it's not one of our original ones, but that's one we're going to be working with now. If we had another equation with just x and y in it, we could work with that. We know how to solve systems of two equations with two variables. So we could use equation 1 and equation 3 and get rid of the z using those two. So we used 1 and 2 the first time, now we're using 1 and 3. conveniently, they both, if we add those together, we'll get rid of z. In real life, you'll usually have to multiply one of these by something or multiply both of them by something, but we'll be doing some of those later. For now, we have this one that's easier. Add those two equations together and we get this. We'll call it equation 5. Okay, and it doesn't have any z's in it because we eliminated the z right there. So now we have equation 4 and equation 5. 4 is this one, 5 is this one. They have only x's and y's, so we write them down here. And boy, these guys were clever, because it just works out that we don't have to multiply by anything. We add these together, the x term will be gone. All we'll have is y. So we add them together, then solve for y. We have y equals -5. So that's great. We've done enough work to solve for one of the variables, and now things start falling into place, because you can take that and substitute it in, and for y in the equations, and have at that point an equation that doesn't have a y in it and just has the other variables. So the strategy we're going to use here is we'll do that in two different equations to get equations that just have x and z. Okay, because we only have y is the only one we've solved for yet so far. We still need to solve for x and z, and what we do is we take equation 1 right here, plop that, see, that's this one here, plop that value for that we found for y into it, substitute it in for y, so that's right here, right? It was -y, but now it's minus -5. We put in -5 for y, and then we have an equation that only has two variables, x and z. So we just simplify that. Minus -5 becomes +5. Add 5 to both sides, and there you have it. And we'll call that equation 6. Okay, it's another equation we've obtained. It only has x and z in it. Well, we could use a different pair of equations, and let's see, I should have drawn a line under that. I'm going to have to switch back to blue. Go about right there, that color, to show we've done that subtraction. Okay, and down here we're going to have the same thing. Whoops. Go back to my other color, see if I can get it where it was. Okay, so yeah, we have a number 6. Equation 6 has just x and z. We want another equation that just has x and z. We used 1. Oh, I didn't label this one. Oh, we used 1. Yes, I did label it. Sorry. What have I done? I made a mistake. I don't want those lines there. All we did here was substitute. Sorry about that. We weren't adding equations or anything. That's why I didn't have lines there. So we substituted into equation 1, and we got equation 6 that just have x and z. Now we're going to substitute into equation 2. Put y in, y equals -5 into it. Okay? Because we had 4y, so that's where we put in the -5 for it. And then it only has x and z, the only variable. That's good. Take the 4 times negative 5 is negative 20, add it to both sides, and here we could call this equation 7. It has just x and z. We already had equation 6 that has just x and z. Things are getting there. We're making progress. So, as you might expect, we have those two equations that just have two variables, x and z. We can now use elimination on them. And it must have been a lot of fun designing this problem, because after all this work, it's very convenient. It turns out we can add these together to get rid of the z. We don't have to do any multiplying, because they've obviously done this intentionally, which was very kind of them. We add these together and we get rid of the z. We just have 2x equals 12. Solve for x by dividing by 2, and now we have x equals 6. So we have the ordered, we're almost there to get the ordered triple. We have our y and our x. Okay, we got y and then we got x. The last thing we do is over here. We just need z, and now we can use any equation that has z in it because we know x and y both, right? We can plug them in. So what we did was we took equation 1. Okay? And so right here, that's what we did. We took equation 1, we plugged in x and y, right? We know x is 6 and we put it in there. We know y is negative 5 and we put it in there for y. And then we just solve for z. So you go ahead and take the negative 3 times 6, get negative 18. Take minus the negative 5 is positive 5. That's what that is. Minus z, we can combine negative 18 and 5, get negative 13. Add that to both sides, you get 1. So negative z equals 1, so z equals negative 1. And that's the last piece of the puzzle. We now have our ordered triple because we have x is 6. Okay, y is negative 5, z is negative 1, and that's our ordered triple, and that's our solution. Okay, so you're strategic. You combine. You start out in using elimination to whittle it down to a couple equations that just have two variables. We eliminate the z, and then get equation number 4. We eliminate z using a different pair, 1 and 3 this time instead of 1 and 2, to get equation 5, which just has x and y, and then combine those to solve for one of the variables, in this case y. So that's a 3 by 3. That is 3 equations, 3 variables. And computers can do these very easily. They can do 4 by 4. 4 equations, 4 variables. 5 equations, 5 variables. They don't care. And in real life, there are systems that are huge, that have many variables. But we probably won't be doing any that large. But the process is similar. You just keep whittling away at it, eliminating variables. So that's it for this one. See you later.